Alright, we pick up where we left off last time and discuss the very special case of the maximum static friction force. Now, let's go back and take a very quick look at our little diagram for the microscopic case. And here you had these rough edges that were smashing into these rough edges of this block, as this block is attempting to be moved that way. And when this piece hits that, it gets a normal force. When that piece hits that, it gets a normal force. And when this hits this, it gets a normal force. The key thing is that the friction force is created by an interaction between this block and this table. So therefore, the force, this friction force, depends on how these little normal forces add up. And if we add them all up, I said in the previous video that there's some net force. Let's call that the sum of all these little n's, however many there are, from I equal 1 to whatever number. And when you add all those up, what you're going to get is that you're going to get an arrow, and that arrow is going to have two parts. One part, that part creates the normal. The other part creates the friction force. So because these two are related to this arrow, it makes sense that the friction force is related to the normal force in some way. And in fact, in moving friction, as I've just kind of showed where it moves, that's true in general. In the case of the static friction, it's only true for the maximum static friction force. And it's more complicated to try to understand why that is, and I won't, but I will show you in a demo that this is in fact the case. So what's equally important to understand is that there's no statement here about weight. Weight is the interaction between the block and the earth. That has nothing to do about the interaction between the block and this table. So there's no reason to believe that there's any connection between friction and weight, and in general there is not. The only way that there is any connection is if the normal force is connected to the weight through Newton's second law, and that's just purely by chance of things working out that way. All right, on a situation. But there is no general connection between friction and weight. There is a connection between the maximum static friction force and the normal force, because they occur due to the same physical phenomena, these little bumps banging into each other and having interactions between their electrons. Fundamentally, you know, we're talking about atoms, and in chemistry we know there are these things called electrons. These electrons interact. So how they interact depends on their geometrical positioning, therefore how big the bumps are. And it also depends on the type and number of electrons in the atom and how they're bound. So it's going to depend on the two types of material, the material of this block and the material of this table, if you would. All right, let's put that sort of thing down here in this statement about the maximum static friction force. And here's what we can say about it. So the magnitude of the maximum static friction force is directly proportional to the magnitude of the normal force acting on the surface. What does that mean? This directly proportional thing. It means that that force and there's the statement mathematically, is directly proportional to normal. If you double this normal force, you double the static friction force. And by the way, I'm going to put max there because it's only true for the maximum. If you triple the normal force, you triple this force. If you make it 4 times larger, you make this 4 times larger. It doesn't say that if this is 10 newtons, that's 10 newtons. This could be 10 newtons and that could be 5 newtons, and when you made this 20 newtons, then this becomes 10. If you double that, you double this. But in order to make this not a proportional, to make it equal, you have to have some constant added. In mathematics, what that says is that to make this an equal, you must add some constant in front of that, like this constant. And that constant has a name. It's called the proportionality constant. Well, that proportionality constant is a constant only if you keep the things in the experiment the same. Just like in the case, for instance, mass is a proportionality constant between force and acceleration. But you can have objects that have different masses. You can have things that have different proportionality constant. It depends on the physical property of the two objects, what they're made of, how smooth and rough they are. For instance, sandpaper is very rough. It has a big proportionality constant. Ice is not as rough. It has a lower proportionality constant. We actually give this proportionality constant a name, just like we give the proportionality constant between force and acceleration a name. We call it mass. Well, there's one similar here. It's called the coefficient of static friction. And we don't use the symbol K, just like we don't use the symbol K in the case of force and acceleration. We use M. Here we're going to use a Greek M called mu. So this coefficient, the symbol for that is mu, and generally there's a little s because there's a coefficient of kinetic friction. So most of the time they put a little s to tell you they mean static. And we can put all of this in mathematics as follows. We could write that the static friction is less than or equal to mu s times the normal. I'll put a little s to indicate static. But that's not a very useful thing because that's an inequality. It's not an equal. It's true. It states everything about it. It tells you what the maximum is. It tells you that if it's less than the max, then it's some value less. But more useful is just to write the formula where you can use it. When you're talking about the maximum static friction, you may use this thing, the coefficient of static friction times the normal. However, be careful. If it is not the maximum static friction, this formula is not true. All you know is that it's less than this. Now, how do you know that it's the maximum static friction? Usually there's something in the problem that tells you that. For instance, the object is just beginning to slip. It hasn't slipped yet, it's just beginning. So at that point, it has no acceleration, it has a maximum static friction force. At the point that it just starts to slip, what is the coefficient of static friction? Obviously, they're asking you to solve it at the case where there's the maximum static friction. But if you don't see things like that in the problem, the object is just sitting at rest on an inclined plane, you cannot assume that it's at the maximum static friction. So be careful. These are the ones that get students. All right? There has to be something that tells you you're at that location at this maximum and not at some place where it's less than this. If you substitute mu Sn in for F, then you've assumed that it's at the max, and that may not be the case. So be careful. All right, so we'll give you some example problems in your notes elsewhere. I'll leave that till then. That covers this part of static friction.